Okay, in this question you'll follow the thoughts that convinced Sir Isaac Newton of the universal law of gravitation. Let us first consider an apple falling near the surface of the Earth. An apple, when released from rest, accelerates towards the centre of the Earth at approximately 10 meters per second squared. Show that the apple will fall 5 meters in 1 second. So, assuming acceleration is constant, we can use a Seebeck equation. It says it starts from rest, so u is 0. Plug the numbers in and we come out with 5 meters. So the Greeks showed that the moon is roughly 60 times further from the center of the Earth than an apple at the Earth's surface. Newton expected the acceleration due to the Earth's gravitational force at the moon's orbit to be smaller than that of the surface of the Earth. But the question was, how much smaller? 60 times? So Newton had remarkable intuition and expected acceleration due to gravity to not be 60 times smaller, but 3,600 times smaller, so to follow an inverse square kind of relationship. Show that the moon must fall approximately 1.4 millimeters towards the center of the Earth if it initially has 0 velocity in this direction. So we're basically doing exactly the same question, but changing the acceleration to 10 divided by 3,600. And that gives us our value there of about 1.4 millimeters. Okay, so the moon takes approximately 28 days to orbit the Earth at a radius of 384,000 kilometers. Show that the speed of the moon in its orbit is approximately 1 kilometer per second. Okay, so first of all I'm going to convert 28 days into seconds, and then the distance it travels is going to be the circumference, so 2 pi times by r, and that gives us our speed in kilometers per second there. Okay, so what is the distance AB if the moon reaches point B 1 second after being at A? So if we assume the speed to be constant, we can just do distance is speed times time. So after 1 second, it's going to have travelled a distance of 1 kilometre. That makes sense. Apply Pythagoras' theorem to show that using distances measured in kilometers, we get this relationship here. So you'll notice that we formed a right-angled triangle. So OA is the radius, the 384,000 kilometers. AB is 1 kilometer there. So essentially what you can do is get an expression for the hypotenuse. Okay, so what we're going to do is Pythagoras' theorem, so r plus x, so O to C is the radius and C to B is what we've called x. So that whole distance squared should be equal to OA, which is r, so r squared, and AB, which is 1 squared. That's just using Pythagoras' theorem. Multiplied out the brackets, we can collect the terms and we can cancel the r squareds, and we can see we do indeed end up with the expression that we've got there. Okay, so using the expression from the previous part, show that a fall of 1.3 millimeters each second is necessary to describe the motion of the moon in its orbit. So within the approximations made, this is equal to the answer in B. Okay, so let's first pick up the equation that we've just come up with, and I'm going to rearrange that to make it in a normal quadratic form that you see equations, something equal to 0. Now I'm going to use a trick that is actually used a lot in mathematics, physics, engineering, and it's very useful to use. I'm going to assume that x squared can be ignored because x is really small, so x squared is going to be tiny and insignificant. So we're going to ignore x squared, and that simplifies the problem to this. And then once we do that, we can solve for x, and you can see that yes, it does in fact come out around about the 1.3 millimeter value that we've seen before, and that finishes this question.